So, let us talk about debugging and what debugging could be. So, if you've used a debugger on your program, when you're trying to figure out what's going wrong, often there's some problems with that. You have to set a point in your program where it's going to be interrupted and you can stop and investigate the current state of your program. And that's great if you know precisely where you need to stop in order to figure out what the problem is. But if you stop too early, then it takes longer to reach the point where you actually care about and you need to be able to figure out what's going on. However, if you leave it too late, you can't investigate earlier state in the program and you have to start all over again from the beginning. So that's really annoying. There's a third problem too, and that is, what if the error does not actually reproduce every single time you run the program? Because suddenly, if you need to restart your program, you no longer are able to be sure that it's going to reproduce at the point where you stop the program, and you might have to run it over and over and over. And that is very frustrating. Because in this case, you've encountered the specter of non-determinism in your program. And that is a terrible thing to encounter. So let's talk about what determinism means in a computer program. That's when you have code that is only affected, the behavior of the code is only affected by the state that is present in your program when it begins to run. And that means it's either data that is present inside your program already, or is provided by the user as an argument to your program. So here's an example of something that is deterministic, which might not look deterministic at first, because it uses a random number. And a random number, as we know, it's not always the same value, because every time you call it, you'll get something different. However, what's important here is that, despite the fact we're using a random number, we seed our random number generator with a value that is provided by the user when the program runs. So that means that if I start this program and provide it the value 5 on the command line, that will seed the random number generator with the value 5, and every time I run that program with the same value of 5, we'll get the same sequence of random numbers that are generated. That means that the program will behave exactly the same every single time we run it. That's a useful property. However, a more sensible way of writing code that uses random numbers is that if you want actual randomness, you should probably seed it with something that is not going to be the same every time. So in this case, if you write a program that uses the time command, or the time function in C, we can use the value of the current time when the program executes to seed the random number generator and get different random numbers every time we run it, regardless of what arguments we pass. This program is non-deterministic because we cannot guarantee the same behavior every time you run it. So non-determinism is caused by things that are outside of the program. They're caused by the user providing input that the program has to wait on or retrieve in some way. It's caused by scheduling. If you have multiple threads in your code, the operating system can choose to schedule some of the code before other code, or reverse that depending on what time of day it is or how busy the computer is. If anything else interrupts your program via an external signal, such as the user pressing Control-C, that can change the behavior flow of your program. And again, time. That always continuously moves forward, and if you involve time in your programs, it's going to be non-deterministic for that reason. So I want to tell you about a tool that's been developed by people who used to work for Mozilla and now are working entirely on this project. It's called RR, and that stands for Record and Replay. And the idea behind this tool is that it records non-deterministic executions, but then replays them in a deterministic manner. So you will always get the exact same behavior from your program every time you run it after that point. And so what this means is that your sessions of debugging are no longer just snapshots in time where you lose everything if you move forward. Now your debugger is actually an elephant. It can remember everything that came before it. And you can travel through time, backwards and forwards. So, that's an easy thing to say, but let's see what that looks like in practice. So what I have here is, what was I looking for here? I'm going to run this simple web server, which was put together, which has, that was the wrong window. Virtual machines, who knew? So this web server has a problem. I can run it, and I can refresh it over and over, but occasionally, once in a while, every so often, sometimes it doesn't work, and that's quite mysterious. So, as it happens, I've previously made a recording of this session, of encountering that error, and I noticed that in my terminal here, which I can pump up, when an error happens, it conveniently prints out this message that says an error occurred. So I say, okay, I can use my debugger and I can find the code that actually prints out that message, and that'll show me where to start. So let's look where that happens. And so in this code, you see, oh, okay, it prints out when it checks this thing, but likely the place where it's actually checking where an error occurred and whether to print out a message is not actually where the error occurred as such. So that's not so good, because if I stop there in a normal debugger, that's after the error occurred, and that won't help me. However, that does not have to stop us anymore. I will start my replay server, and then live demos. So that was the line I was just looking at. And like a usual debugger, this integrates with GDB, and it can now show me the code that I am looking at. So you'll note that we have stopped the code in this session that I previously ran at this place that said an error occurred. Now, usually a debugger can go like next line, we can investigate what's happening step by step. However, with RR, we can go backwards. What? This is super cool. Okay, now let's look at something more interesting. So we want to find out where this error was actually set. So we can go, okay, where is the memory stored for this error value that is stored? And let's go, okay, let's set a watch point on this memory so that we'll interrupt the program when the memory is modified. And then, let's just run the program backwards until it happens. What? Suddenly we have a breakpoint that went back in time to the place where the flag was set. And that means that we can go, okay, so we know that this value is null, so let's figure out where this came from. So we'll go backwards over the place that it came from, and then we'll step into it going forwards, and we can go forwards, and we can go forwards, and we can go, oh, let's see what MC is now. Oh, it's null. Okay, so we need to go backwards again. Good thing that we can do that. And we can step into this, and we can go like this. We can see, what is con? Oh, it's also null. Let's go backwards again. So if we do that, we can step into this one, and suddenly we see that there's this alloc connection function. Let's take a look at that, what that does. We'll step into it. Oh, a random number. Whoa, who could have seen that coming? Serious. And it turns out, if we step through this, you know, it happens that this is the value we were looking for, and we return null here. And we can go backwards, and we can step into it again, and we get the same number every single time. We can even just like run the program from start and continue again, and we'll skip over that. But the point is that we can do this again. We can run the same steps over and over. We'll get the exact same values. The pointers are the same, so the watch point remains usable every single time you run it. And it's really, it's so empowering to be able to travel backwards and not just have to restart the session over and over. It's really quite something. So, really, like, that is kind of spooky if you're used to just using regular debuggers that only go forwards in time. So there's a few tricks here. One is that, like I said, scheduling is an important thing when avoiding non-determinism. So therefore, this tool just takes all the threads and puts them on a single CPU and says, okay, only one piece of code can execute at a time, and therefore, if we record the order in which the code executes, we can replay that and say that we'll replay the code execution in the same order, so we don't have any scheduling problems. Additionally, anytime a program would communicate with the operating system, such as printing output, getting input, when recording the program, we note every time that happens, and we note the response the operating system gives us, and we store that in a trace file. And that means that later, when we're playing the program, we can say, oh, at this point in time, when we are about to go and talk to the operating system and like print out something on screen, instead of actually talking to the operating system, we pretend we do. We know exactly what the operating system gave us last time, so just intercept that, pretend it happened, and store the results from the operating system in the place where the program expects to see them, and continue executing. It's like a little sleight of hand. Additionally, you need some way of being able to tell precisely when in time something happens. So you can say, at this time, intercept this call, provide this data, and then you can do that sleight of hand. So there are performance counters that provide this monotonically increasing value that we can query at any time when recording, so that we have something, a scale of time that we can use. And that's all there is to it, really. There's a lot of complications on top of that, but that is the basic theory. It's just about lying to the operating system instead of having the operating system lie to us. So why R is special? It's really good at its job. This isn't the first time someone's written something like this, but it's really good at being used at scale on programs like Firefox. We've solved a lot of bugs with it, and in really complex ways, in dealing with things like media graphs, things where time makes a difference, and using a regular debugger, that's a problem if you just pause there for a while because you have code saying, oh, it's been 5 seconds since the last time I did something, now everything's changing. This just replays time the way it happened in the original program, which is very useful. It's open source. It's at the RR project account under the Mozilla organization. The things that this can enable are really neat, because it means that because it is so efficient at its job, then it can be used to run all your tests all the time, and instead of having occasionally flaky tests, you can just say, oh, we have a recording of that particular session, we'll just go investigate what the problem was. And then no more intermittent test failures. Additionally, you can use it on optimized programs, and instead of using your debugger and going, oh, it doesn't understand where this value is, it was optimized out, it doesn't understand this one, you can just go back in time to determine the source of that value, and it just works. So, consider whether your work could be enhanced by traveling through time. Thank you.